means that there's going to be much more sun absorbed. Will explode. It's trying to talk to us, but we can't hear it. Okay, well they don't seem to be doing very much now, so I might get on, because we do have to cover some stuff that's still going to be in the exam, I'm afraid, whether or not we have robot company. Alright, so I think I've covered this. We've got an effective... The same stuff is still in the exam, I tell you, the exam is good. It's like being in a very...
Hi Simon, we are the police. We are looking for a couple of rogue robots. We are pretty sure they have become self-aware.
It's like being on a very long episode of Doctor Who. So, last few things, right? So, one of the things that you have to take into account is that the light that's hitting a solar panel or the surface of the Earth is not just the direct sunshine, okay? So, so some of the sunlight is actually scattered towards the surface of the Earth, and you have to take into account what's called diffuse irradiation separately from...
Let's start it off.
It's talking to the other robot. I think they might be making love. I think it's okay. This one's doing a little spiral here. I think it's got lost. Try and go through this quickly. I've got 5 minutes. So, if you think about a solar panel, you can obviously make some improvements to the amount of energy it's going to absorb by which angle you tilt it to. And in principle, this is a relatively complicated problem because there's actually quite a lot of angles involved. So the azimuth angle is the angle, is that angle. So you've got a solar panel tilted relative to the surface of the Earth. The angle that it's tilted at, is gamma p. So that's the angle gamma p, the angle between the solar panel and the surface of the Earth. The azimuthal angle is the twist. So I'm assuming you're the sun. Okay. So the formulae that are given here allow you to calculate the energy reaching the solar panel compared to the energy when the solar panel is lying horizontal. So these are kind of weird formulae because they behave in a slightly, well, particularly this one, behaves in a slightly odd way. So I just want to try and talk you through how this works in terms of this angle theta and the angle gamma s. So okay, this is a bit more complicated than we need. Let's focus on the simplified version of the diagram. So gamma s is the same angle that we had a few slides ago. It's the angle that the sun's rays make with the surface of the Earth. It's stuck. So it's the angle the sun rays make with the surface of the Earth, whereas theta is the angle made with the normal, the right angle to the solar panel itself. Okay, so that's theta, and this is gamma s. I'll put it out of its misery. Alright, so if we look at this, remember these equations are working relative to the radiation received when the solar panel's lying flat. So when the panel's lying flat, it's clear that the effective area of that solar panel is lower than when it's pointing perpendicular to the sun's rays. It's clear that the most efficient way of positioning the solar panel is going to be perpendicular because that maximises the maximum area. It's very difficult to do this. Amazing how one more member of the audience can put you up again. Right. So we can see that there's going to be a gain in the effective area when we tilt the solar panel up. So that means that compared to the energy that we were generating when the solar panel was lying flat, we're going to have a gain which is 1 over sine gamma s. So sine of gamma s is going to be a number smaller than 1. 1 over sine gamma s is a number bigger than 1. So that's a gain in energy. Okay? But now, if we go from this position of being perpendicular to the sun's rays and tilt the solar panel back, so that means that the normal here is tilted back in this direction, and we're creating an angle theta between the normal and the sun's rays, we're going to see, we see that there's a decrease in effective area by the angle cos theta. So now you've got this kind of odd dependence in this equation between cos theta and sine gamma, and you can see on the next page that this equation does actually make sense. Because if you look at this diagram, if you add up gamma s, theta, 90 degrees, and gamma p is the angle the solar panel makes with the surface of the ground, you can see that they all have to add up to 180 degrees. So that's what this equation is here. Gamma s, theta, 90 degrees, and gamma p all add up to 180. We can rearrange that so that theta is 90 minus gamma s minus gamma p. And that means when we lie the panel flat again, and gamma p is 0, and theta is 90 minus gamma s, we've got this formula here has got a cos theta in it. Cos of 90 minus gamma s is the same as sine of gamma s. So if we put into this equation sine of gamma s instead of cos theta, we get back to the same equation. So the equation works, and it tells you the amount of radiation reaching our solar panel as a function of this angle gamma s, and as a function of the tilt relative to the normal. Okay, so this works well. This equation here asks you to use these equations. This problem asks you to use these equations, and you can find anything. You should practice using these equations. You'll find that the correct answer